This call is now being recorded.
पुढं पुढं कुठे दिसते पुढं Okay, now we move towards next chapter, chapter 5, structure of process. What is the structure of this process? In this chapter, we are going to study that is process state and transitions, layout of system memory, the contents of process, the saving context of a process, and for this chapter, a textbook is a design Unix operating system by Maurice J. Batch by PHI publication, and CO is student will be able to describe structure of process. So what is important of this chapter in your syllabus? That is a structure process. Process is a part of program. It is instance or it is a part of a program. It is instance of that program. And structure will give employee more clarity, help manage expectations, enable better decision making, provide consistency with organizational charts, also assign responsibility, organization flow, and sure importance or task completed on time. And you are studied in operating system first, that is operating system concepts. What is a process? Then process a table, different parts of process, process state transition diagrams you have studied. So in Unix system there is process state and a transition. So life of process or lifetime of a process can be conceptually divided into set of states. So you have studied such as there are process state process state transition diagrams. There are states, that is newly born process, then ready to run, then executing process, or end of that process terminal, or some processes going to sleeping or waiting state. So here in Unix system there are a list contains a set of process states such as process is executing in user mode as well as in kernel mode. Process is not executing but ready to run as soon as kernel schedule it. First state is process is executing in user mode and in kernel mode. Second, process is not executing but ready to run whenever kernel schedule it. Process is sleeping and resides in main memory. Process is ready to run swaps, that is the process into main memory before the kernel can schedule it to execute. Process is ready to run, but the swapper must swap the process into memory before kernel can schedule it to execute, and the process is sleeping, and the swapper has swapped the process into secondary storage to make room for other processes in main memory. Then process is returning from the kernel to user mode, but kernel preempts it, does a context a switch to schedule another process. Whenever process is returning from user mode or kernel mode to user mode, but kernel preempts it and other process is scheduled for execution. So process, the next part, process is newly created and it is in a transition state. Process exists but not ready to run, nor it is sleeping, and this state is a start state for all processes except process 0. Whenever a process is newly created and it is in transition state, the process exists but not ready to run, nor it is sleeping. So this state is a start state to all processes except process 0. The process is executed in exit system call and is in the zombie state. The process is no longer exists, but it leaves a record containing an exit code and some timing statistics for its parent process to collect. And the zombie state is the final state of process, that is executing state. The process is no longer exist, but it leaves a record containing an exit code and some timing statistics for its parent process to collect. See this figure, that is a process state a transition diagram. See this figure carefully. See in this figure, there are eight states. First, a state that is user running mode. Second state is kernel running mode. Then a third state is ready to run in memory. Fourth state go to the sleep in memory mode. Fifth state is ready to run a swapped. Sixth step is sleep swapped. Seventh step is preempted, and eighth state is created. Ninth step is zombie, that is execute. So the process is running in both kernel mode as well as user mode. Whenever a system call in interrupt, so the process goes to from user mode to the kernel mode. Whenever the process is executing or running, and it goes to the preempt, that is a preempt state, that is a seventh state. After preemption, it goes to the user mode, and from user mode to the kernel mode for execution of that process, that is a zombie state. Sometimes a kernel interrupt that process or interrupt the system call to that process, so there is a loop. Whenever number of processes are preempted or going to execute state, so some process are go to sleep mode in main memory, that is fourth step. From fourth step, after some time some processes wake up, so go to the third step, and there is a reschedule of that process for execution. So these processes are ready to run in main memory. Okay, but some processes are swapped out in sleep mode, swapped at sixth step. So these processes after some time wake up from sleep mode and are ready to run a swapped out. So go to the swap in, that is go to the ready to run in main memory. Whenever a new process is created, that is due to fork system call, so not enough memory, so they are swapping system only, go to from 8th system to 5th system. If there is enough memory, then go to ready to run, then reschedule that process and go to the kernel mode. If there is kernel is not busy, then execute that process. So this is a general structure of process a state transition diagram. We'll see in detail. So this figure shows the complete process state transition diagram. This figure consider this typical process. It moves through the transition model. The events as shown in this process state transition diagram does not always experience them, but they illustrate various state transitions. The process enters in state model is called as a created state, that is C here, by fork system call at process step number 8. By fork system call, we can generate a new process. When the parent process executes the fork system call and eventually moves into state where ready to run, either go to the step number 5 or step number 3. If there is enough memory, then it goes to the step number 3, that is ready to run in memory. If there is no enough memory, then it is goes to the swapping. So for simplicity, assume that the process enters into the ready to run memory, that is go to the process number 3. The process scheduler will eventually pick up the process to execute and enters in kernel ready kernel running. So for rescheduling that process execution where it completes its part of the fork system call. So when process complete the system call, it may moves to the state user running mode where it executes in user mode. After some time, the system clock may interrupt that process and enters in kernel running mode again. See in this figure. So whenever the process is newly created, if there is enough memory, go to the ready to run in main memory and reschedule the process execution, so it enters into the kernel running memory and goes to the user running mode. And after user running, after sometimes it goes system call interrupts, it goes to the kernel mode for execution. So when clock interrupts handler finishes servicing the clock interrupt, the kernel may decide the schedule another process to execute. So first process enters in the preempted and other processes execute. So preempted is really is same as the set ready to run in memory. So here in figure dotted line in that figure connects two states are equivalence. See here from ready to run the process can enter from third state to seventh state, that is go to the preempted state. Whenever the newly created system calls enters into kernel running mode, but the kernel executes other processes at that time, so this process goes to the preemption state. So when from preemption state to again goes to the user running state and then again to the kernel running state for executing that process. Eventually the scheduler will select the process to execute and it returns to the state user running, executing in user mode again. When process executes a system call, it leaves the state user running and enters to the state kernel running. Suppose the system call requires input output from the disk and the process must wait for input output to complete. So it enters the state asleep memory, putting itself to sleep until notified that input output has completed. See in this figure. Whenever the newly created process after preemption enters to the running mode and after the system call enters from user mode to the kernel mode, but there is no number of processes are waiting for execution at that time, the newly created process go to the sleep mode in main memory. So when the IO latter completes, the hardware may interrupt the CPU and interrupt handler awakens the process causing the enter state ready to run in main memory. That is a scene figure. Whenever the required input output hardware is available to that process, then wake up the process that is ready to run, go to ready to run in main memory state, reschedule the process and go to the kernel running mode for execution. Suppose the system is executing many processes and do not fit simultaneously into memory, and the swapper, that is process 0, swaps out the process and makes room for another process in that state that is ready to run a swapped. When evicted from the main memory, the process enters a state ready to run swapped. See in this figure, when there is no space in memory, then the process is swapped by process 0 and go to the sleep mode. Whenever the input output or other hardware part is available for execution, that a swapped process wake up and ready to run a swapped. So go to the swapped in from step number 5 to step number 3 for ready to run in main memory, then reschedule that process and execute. Go to the kernel running mode for execution. So eventually the swapper selects the process as the most suitable swap into main memory, and the process re-enters the state ready to run in main memory. So the scheduler will eventually select to run the process and enters the state kernel running and proceeds. When the process completes, it invokes the exit system call, thus entering the kernel running and finally to zombie state. The process has control over some state transition at user level. So first, a process can create another process, that is by using fork system call. However, the state transition process takes from the created state, that is, the state is ready to run in memory or ready to run swapped, depends on the kernel. See in this figure, whenever the process is created by fork system call, there are two ways for execution that process. If there is enough memory, then they are going ready, go to the third step, ready to run in main memory for execution. If there is not enough memory, then go to the swapped state by using swapping system call at step number 5. The process has no control over these state transitions. Second, the process can make system calls to move from state user running state to kernel running, from user running state to kernel running state. So process can make system call. Due to interruption of system call, the process moves from user mode to the kernel mode, enter in kernel its own valuation. However, the process has no control over when it is returned from kernel. Events may dictate that it never returns but enters the zombie state. Finally, a process can exit its own valuation but indicated before, external events may dictate that it exists without explicitly invoking the exit system call. Another state transition flow, a rigid model encoded in kernel, reacting to events in predictable way according to rules formulated in this and the latter, that is in 6th chapter, 6th and 7th chapter. So some rules have already been cited, that is, no process can preempt other process executing in kernel. If a process is going to in preemption state, then no other process can enter in that state whenever that preemption has been completed. If the process has been completed its preemption, then and then only other processes can enter in that state. So two kernel data structures describe a state of the processes. First is process table entry and second is user area. There are two types of kernel data structures which describes by the state of processes or process states, such that process table entry and the user area. In that, in process table contains fields that must always be accessible to kernel. Process table contains of fields which are accessible to by the kernel, but user area field contains that need to be accessible only in running process, not other processes. The user area fields are accessible to the kernel at the time of the running processes. Therefore, kernel allocates a space for the user area only when creating a process. Whenever a process is created, the kernel allocates space for that newly created process. It does not need user area for the process table entries. So they don't have process and that do not have the processes. This is the general description of process state and transition. So what are the different fields in this process table? This process table contains that is a static field. The state field identifies the process state. The state field identifies the process state. Process table entry contains fields that allow process table entry contains fields that allow kernel to locate process and its user area in main memory or a secondary storage. So whenever the entry in the process table, that is the kernel allows to locate that process in user area in main memory or secondary storage. So kernel uses information to do a context switch. Kernel uses the information to do a context switch to the process when process moves from ready to run in memory to kernel running. Whenever the process moves from ready to run in memory or kernel running, there is a context a switch to the process, or another way, from the state preempted to the state user running. And third, that is in addition, it uses the information when swapping, that is paging process to and from main memory, that is between in main memory states or two swapped states, between two in main memory states or two swapped state. So then the process table entry also contains field that gives the process size. Kernel knows how much space is required for that process. Then user IDs. Several user IDs determine various process privileges. The process table entry contains event descriptor when process is in sleep state. Scheduling parameters. Scheduling parameters allow kernel to determine the order in which process move to the state, that is from kernel running mode to user running mode, or kernel mode to user mode. There is scheduling parameters allows kernel to determine which process moves from kernel mode to user mode. Then signal field enumerates the signal sends to a process. Various timers give a process execution time. Kernel resource utilization used for process accounting and for the calculation of process scheduling priority. Then a different, you have seen the characteristics of process table entry. Now we are going to see the what are the characteristics of user area. So a pointer to the process table identifies a pointer to the process table identifies the entry that corresponds to the user area. A pointer to the process table entry identifies the entry that corresponding to the user area. The real and effective the real and effective user IDs determine various privileges allowed the process such as file access rights. Timer field records the time the process spent executing in user mode and in kernel mode. Then array indicates how the process want to react to this with the signal. Control terminal fields identifies login terminal, allocates with the process if one process exists. An error field records errors encountered during the system call. A return value field contains a result of system call. Whenever a process is interrupted by any system call, then it gives the return value. What is the acknowledgement of that system call? Then input output parameters describes amount of data to be transferred to the address of source or target data array in user space. File offsets for IO and so on. The current directory and current root describe the file system environment to the process. The user file descriptor table records the file the process has opened. Limit restricts a size of process, a size of file it can write. Permission modes, field mask mode, settings on the files process creates. Then next part is layout of system memory. Assume that the physical memory of machine is addressable. Assume that the physical memory of machine is addressable starting at byte offset 0 and going up to a byte offset equal to the amount of memory on the machine. A process on Unix system consists of three logical sections such as a text, data, and a stack. The text section contains set of instructions the machine executes for process. Text section contains a set of instructions the machine executes for the process. The address in the text section include a text address. The address in the text section includes a text address for branch instructions or subroutine calls. Then next part is data address. Data address for access to global data variables, or a stack address for access to data structure local to a subroutine. If the machine were to treat generated access as address locations in physical memory, it would be impossible for two processes to execute concurrently if their set of generated access addresses overlapped. If machine were to treat generated address as address location in physical memory, it would be impossible for two processes to execute concurrently if their generated addresses overlapped. So there is no execution of two processes simultaneously. Then compiler could generate addresses that did not overlap between program. Compiler could generate such addresses during execution of the such addresses of that processes during execution of programmer during execution of programs that processes do not overlap, but such a procedure is impractical. But such a procedure is impractical for general purpose computers because amount of memory on machine is finite. Because the amount of memory during general machines is finite, and set of all programmers that would be compiled is infinite. Even if the compiler used a huge data to that heuristics to try to avoid unnecessary overlap of generated addresses, the implementation would be inflexible and therefore undesirable. So if the compiler used the heuristics to try to avoid unnecessary overlap of generated addresses, but implementation will be not flexible and it is not desirable. So compiler therefore generates addresses for virtual address space with a given address range and machines memory management unit translate the virtual addresses generated by compiler to the address locations in the physical memory. If there is overlapping two processes, ex- uh, execution of two processes is simultaneously, so there is a overlapping of addresses. So compiler therefore generates addresses for virtual address space with given address range and machines memory management so that A translation of address from translation of addresses virtual addresses generated by compiler into the location address location in physical memory. So compiler does not have to know where in main memory the kernel will later load the program for execution or not. Kernel don't know where compiler don't know where in memory kernel will later load the program for execution or not. In fact, several copies of program can coexist in memory. So all execute using same virtual address but reference different physical addresses. So execution of programs done by same virtual addresses but reference copies are different in physical memory address space. So the subsystem of kernel and hardware that cooperate to translate virtual to physical address comprise the memory management subsystem into four parts. First part is a region. Second part is pages and page tables. Third, layout of the kernel. And fourth part is the user area. So we'll study a detail each and every part. First part is a region. The system file kernel divides the virtual address space of a process into logical regions. Whenever the compiler generates the virtual address space to a process execution, so that divides that address into logical regions. So what is a region? Region is a continuous area of virtual address space of process that can be treated as distinct object to be shared or protected. Region is a continuous area of virtual address space of a process. That area can be treated as a different object to be shared or protected. So text, data and stack usually form the separate regions of a process. Text, data and stack usually form separate regions of a process, and so that several processes can share a region. For instance, several processes may execute same program, and it is a natural that they share one copy of the text region. Similarly, several processes may cooperate to share common shared memory region. Kernel contains a region table and allocates an entry from the table for each active region in the system. So each process contains private per process region table is called as P region, that is private region. P region, that is private region or process region table. Private per process region table, also known as P region. So private region, that is P region, entries may exist in process table, the user area, or a separately allocated area of memory. Depends on the implementation, but for simplicity, assume that they are the part of the process table entry. So P region, that is a private per process region table which exists in process table, user area, or separately allocated area of memory depend on implementation, but for simplicity assume that all are the part of process table entry and each p region entry points to a region table entry. each p region table each p region entry point to region table entry and contains the starting virtual address of region process in shared region. The shared region may have different virtual addresses. The shared regions may have different virtual addresses in each process. The P region entry also contains a permission field that indicates the type of access the process. There are some permission entry fields such as a read only, write only, or read write only, or read and execute only. So this P region and the region structure are analogous to the file table and inode structure in the file system. This P region and file and region structure are analogous to file table and inode table in the file system such that several processes can share their part of their address space via a region much as they share access to the file via inode. Each process access the region via private p region entry much as it access the inode via private entries in its user file descriptor table and the kernel file table. See, this is the structure of process and a region. See this figure carefully. See in this figure, there are two processes, process A and process B. This is P region area. This is also P region area. This P region area for process A. This P region area for process B. And this P region area consists of text, data, and stack. So this is virtual address space, and this is in elliptical part is shown as the regions for that processes where in this region A is shared by both process A and process B. So this figure shows two processes A and B, showing their regions, P regions and virtual addresses, where the regions are connected. The processes share a text a region A, that is from process A, virtual address is 8K and process B virtual address is 4K, is shared by the region A. If process A reads memory location 8K, if a process A reads memory location 8K, the process B reads memory location 4K. They read the identical memory locations in the region A. The data region and stack regions of both processes are private. See this data region of process A and the stack region of process A. Similarly, data region of process B and stack region of process B. These data regions and stack regions of these both processes are private. The concept of region is independent of memory management policies implemented by the operating system. Region, that is independence of memory management policies implemented by this operating system, is known as a region. So memory management policies refers to action the kernel takes to ensure the processes share main memory fairly. For example, two memory management policies are the process swapping and demand paging. The concept of the region is also independent. The concept of the region is also independent of the memory management implementation, whether the memory is divided into pages or in segments. Then a second part is pages and page tables. See in this figure, this is the address physical memory pages. So in memory management architecture based on the pages, memory management hardware divides physical memory into set of equal sized blocks called as pages. Set of equal sized blocks called pages. So a typical page size range from 512 bytes to 4 KB, and they are defined by the hardware. So each address location in memory is contained in a page, and consequently every memory location can be addressed by a pair. For example, page number and byte offset in page. For example, a machine has a 2 raised to 32 2 raised to 32 bytes of physical memory and page size of 1 KB. Then it has 2 raised to 22 pages of physical memory. Every 32-bit address can be treated as a pair consisting of 22-bit page number and 10-bit offset into the page. Suppose here in this table, here hexadecimal address is given like this. Its binary format has shown this, that is a binary format is 0101. Then its binary format 1000. Then first binary format 0 100. Then three's binary format 0011. Then two's binary format 0010. So the page number and page offset consist of, that is, half of this binary format is page number and half of this page binary number is page offset. So again in hexadecimal format it will become 161, and this is a page number and page offset is 32. So when kernel assigns physical pages of memory to a region, it did not assign pages continuously or in a particular order. When kernel assigns physical pages of memory to a region, there is no particular order of that pages, or pages cannot be assigned continuously. So purpose of page memory is to allow greater flexibility in assigning physical memory, which is analogous to the assignment of disk blocks to files in a file system. Just as the kernel assigns a block into the file, which increase the flexibility, reduce the amount of unused space which caused by block fragmentation. So it assigns pages of the memory to the region. The kernel correlates the virtual address space of a region to their physical machine addresses by mapping to the logical page numbers in the region to the physical page numbers on the machine. See here, kernel correlates the virtual addresses of the region to their physical machine addresses by mapping logical page numbers in the region to the physical numbers of machine. See in this figure, that is mapping of logical to physical numbers. Here logical page number and here physical page number. So logical page number is suppose a 0, physical page number is 177. So logical page number is 1, physical page number is 54, and so on. So in this there is no continuous range in physical page number, where is continuous range is logical page number. So address in, so since a region is a continuous range of virtual addresses in physical in a program, the logical page number is the index of array of the physical page numbers. The region table entry contains the region table entry contains pointer to the table of physical numbers called as page table. Pointer to the physical page numbers called page table. Page table entries may also contain machine dependent information. Machine dependent information such as permission bits to allow reading or writing of a page, such as to allow reading or writing of a page. The kernel stores page tables in memory and causes kernel stores page tables in memory and access them like all other kernel data structures. See in this figure, this is a virtual address and P region, that is private region for a process. So virtual address, that is 8K, which contains a page table entry, then 32K, which contains a table entry, then for stack virtual address 64, it contains a table entry. So this is a physical address, a table entry of the text, of the data, and of the stack. See this figure carefully. So this figure shows a sample mapping of process into a physical memory. Assume that the size of page is 1 KB. Assume that the size of page is 1 KB, and suppose the process want to access virtual memory address 64,432. Suppose the size of each page is 1 KB and the process wants to access virtual memory address 68,432. So the P region entries show that the virtual address space in the stack region, the virtual address space in the stack region, that is 64K, then F5, then 536, which is in decimal format. Assume that the direction of the stack growth towards high address, direction, the address, see the address of text is going from 137 KB to towards 333 KB. Address for data is going from 32 towards 2000 KB, whereas the address of stack is growing towards 64 KB, towards more than 1000 KB. So the modern machine uses a variety of hardware registers and the caches to speed up the address translation procedure, because the memory references and address calculation would otherwise to be slow. The modern machines use a variety of hardware registers and caches to speed up the address translation procedure because memory reference and address calculation would otherwise to be that is to become slow. And that's why newly machines uses a variety or number of hardware registers or cache memory to speedily transfer the address of that processes for execution. So when resuming the execution of process, the kernel therefore informs the main memory hardware where the page table and physical memory of the process resides by loading the appropriate registers. While resuming the execution of process, the kernel therefore informs to the memory management hardware where the page table and physical memory of the process reside by loading the appropriate registers. And since such operations are machine independent and vary from one implementation to other implementation, the exercise at the end of chapter cite a specific machine architectures. We will see at the end of this chapter. Then next, layout of the kernel. Although the kernel execute in the context of process, virtual memory mapping associated with kernel is independent of all processes. The code and the code and data of the kernel reside in system permanently and all processes share it. Code and data of for kernel reside in system permanently and all processes share it. When the system is brought into service, when the system is brought into service, it loads the kernel it loads the kernel code into memory and sets up the necessary tables and registers to map its virtual address into physical memory addresses. The kernel page tables are analogous to the page tables associated with process. The kernel page tables are analogous to the page tables associated with process, and the mechanisms used to map kernel virtual addresses are similar to those used for user addresses. In many machines, the virtual address space of process in many machines, the virtual address space of a process is divided into several classes, including system and user, and each class has its own page table. When executing in kernel mode, the system permits when executing in kernel mode, the system permits access to kernel address, but it prohibits such access when executing in user mode. Thus, when changing mode from user mode to kernel mode due to interruption of system call, the operating system collaborates with hardware for the permission kernel address reference. When changing mode back to user mode, the operating system and hardware prohibits such references. Other machines change the virtual address translation by loading special registers when executing in kernel mode. See, this is the structure of changing mode from user mode to kernel mode. See the figure carefully. See in this figure, See in this figure, there is a changing mode from user mode to the kernel mode. So this is memory address space which contains page table, virtual address and number of pages in page table. So there is address reference from user mode to the kernel mode, but such address reference is prohibited for kernel mode to user mode. So whenever the process enters from user mode to the kernel mode, the operating system asks for the reference address space. So here see, this is our kernel page tables which consist of the addresses of the processes, and this is the process region per table which is user registered addresses. So this figure gives example of the virtual addresses of the kernel and the processes where the kernel virtual addresses ranges from 0 to 4 m minus 1, 0 to 4 m minus 1, and user memory addresses ranges from 4m. There are two sets of memory management, a triple, one for kernel address and one for user address. That is this first three, that is kernel register triple one, kernel register triple two, kernel register triple three, and similarly for user register triple one, user register triple two, and user register triple three. So system allows address reference. The system allows address reference via kernel register triple only when in the kernel mode, and hence switching mode between kernel and user requires only that the system permits or DENY address reference via kernel register triple. Some system implementation load the kernel into the memory such that most kernel virtual addresses are identical to the physical addresses, and the virtual physical memory map to those addresses in identity function. However, the treatment of the user area requires virtual to physical address mapping in the kernel. Then last part is user area. Every process has a private user area that the kernel access it as if there were only one user area in the system, and that of running process. Kernel changes its virtual address translation map according to execution of the process to access correct area. For accessing correct user area while the execution of the process, kernel change as per requirement. Kernel change its virtual address translation as per the requirement for the execution of the process so that that process access the correct user area. While mapping or compiling the operating system, the loader assigns the variable user area, that is name of u area, that is user area, fix a virtual address, a value of the user area virtual address is known to other parts of kernel, in particular module that does not contain a switch. The kernel knows where in its memory management table the virtual address translation for user area is done, and it can dynamically change the address mapping to the user area to another physical address. The two physical addresses represent user area of two processes, but the kernel addresses them via the same virtual address. A process can access its user area when it executes in kernel mode. A process can access its user area when executes in kernel mode, but not when it executes in user mode. While the process is executing in user mode, it does not access its user area. But whenever the process is execute in kernel mode, then it can access its user area because the kernel can access only one user area at a time by its virtual address, and the user area particularly defines the context of a process that is running on the system. When the kernel schedules the process for execution, when the kernel schedules a process for execution, it finds the corresponding user area in physical memory and makes it accessible by its virtual address. See, this is figure memory mapping of user area of kernel, which consists of address of page table, then address virtual address in process, number of process in page table, and these are the page tables for user area for different processes: process A, process B, process C, and process D. While executing a particular process in user area, then there is no access required of user area address space execution if execution of process in user mode, but execution in kernel mode, then there is accessible of user area is required. So in this example, suppose user area is 4 KB long and resides in kernel virtual address 2M. This figure shows a sample memory layout where first two registers, that is a triple registers, refer to kernel text and data, and third triple register is user area, refers to the user area for process D. If kernel want to access the user area of process A, if kernel want to access user area of process A, it copies the appropriate page table for user area into the third register triple. At any instant, the third kernel register triple refers the user area of currently running process, but the kernel can refer to the user area of another process by overwriting the entries for the user area page table address with the new address. The entries for register triple one and triple two do not change for kernel because all processes share kernel text and data. There is a change only in a stack, that is user area. The next part is context of a process. The context of process consists of contents of its user address space and contents of hardware register, kernel data structure that relate to the process, context of process which contains of three parts, that is address space or user address space, the hardware register, and kernel data structure which relates with the process. Formally, the context of a process is union of its user level context, register context, and a system level context, that is kernel data structure. The user level context consists of process text, data, and user stack. With the user level context consists of the process text, data, user stack, and shared memory occupied by virtual address space of a process. The part of virtual address space of a process that periodically do not reside in main memory because of swapping or paging still constitute a part of user level context. So context of a process which consists of following parts. First, the program counter specifies address of next instruction. The program counter specifies the address of next instruction the CPU will execute. The address of virtual The address is a virtual address in kernel or in user memory space. The process status register, that is a PS, PS for processor state status. PS register specifies the hardware status of the machine and it relates to the process. For example, the PS usually contains subfields to indicate that the the recent computation result of recent computation resulted into zero, positive or negative result, or that register is overflowed and carry bit is set and so on. The PS result contains subfields to indicate that a result of that recent computation is either zero, positive or negative, or register overflowed and carry bit is set and so on. So operations that called by peers to be set were are done for a particular process and hence peers contains the hardware status of the machine as it relates to the process. Other important subfields typically found in peers that are those indicates the current processor execution level and the current and most recent modes of executions such as user and kernel modes. Then subfields that shows the current execution subfields that shows the current execution mode such as user mode or kernel mode determines whether process can execute privileged instruction and whether it can access kernel address space. The stack pointer contains the current address of next entry. The stack pointer contains the current address of next entry in kernel or user stack determines the mode of execution. The machine architecture detect, dictate whether the stack pointer to the next free entry on stack or the last used entry. Similarly, machine dictates the direction of stack growth towards numerically higher or lower addresses, but such issues are immaterial for the purpose of this discussion. The general purpose registers contains the general purpose registers contains data generated by the process during this execution. To simplify this discussion, let us distinguish two general purpose registers, register 0 and register 1 for additional use transmission information between the process and the kernel. The context of a process, the kernel pushes the context layer when an interrupt occurs, when a process makes call, and when a process does a context switch. It pops a context layer when kernel returns from the handling the interrupts, when process returns to user mode after the kernel completes execution of the system call, or when the process does a context switch. The context switch thus entails a push or pop of system level context layer. That is, kernel pushes the context layer of the old process and pops the context layer to the new process. The process table entries stores necessary information to recover the current context layer. See, these are the different parts of this context of process. See this figure carefully. See in this figure, this is left side part which chart or table contains of the static portion of context, and right side table contains a dynamic portion of context. So in static portion of context there are again two parts, user level context and static part of system level context. In user level context, a process, a text, data, a stack and shared data. Similarly, then in static part of the system level context consists of process table entry, user area, and pre-process region table, that is P region table. Then this dynamic portion of context consists of different layers, which is dynamic portion. So at zeroth level for the user level, zeroth context, zeroth level for user level, layer 1, layer 2, layer 3. So kernel stack for each layer, and this a static portion layer context is which has, that is, process table entry, which is a logical pointer current context of this layer as shown in this figure. So figure shows the components that of the context of process. Left side of figure shows the static portion of the context. It consists of user level context, which contains process text, that is instructions, data, stack and shared memory. And the static part of the portion, system level context, contains a process table entry, user area and P region entries. The right side of this figure shows a dynamic portion of the context, which consists of several stack frames where each frame contains the saved register context of previous layer, and the kernel stack as a kernel execute in this layer. The system context layer 0, which is a dummy layer that represents the user level context. Growth of the stack here is in user address space, and the kernel stack is null. The arrow pointing from static part of the system level context to the top layer of the dynamic portion of the context, which represents logical information stored in the process table. Logical information stored in the process table entry that to enables kernel to recover the current context layer of the process. So then a process runs within its context. A process runs within its context, or more precisely, we can say within its context layer. The number of context layer is bounded by number of interrupt levels the machine supports. For example, if machine support different interrupt levels for source interrupts, terminals, disk, all other peripherals, and the clock, it supports 5 interrupt levels, and hence a process can contain at most s- 7 context layer. If a process contains of 5 interrupt levels, at most the process can contain 7 context layer, one for interrupt and one for system call, one for each interrupt level 1, one for system calls, and one for user levels. The 7 layers are sufficient to hold all the context layers even if the interrupt occurs in worst possible sequence, because an interrupt of given level is blocked while the kernel handles the interrupts of the level or higher. Although the kernel always execute in the context of some process, the logical function of the logical function that it executes does not necessarily pertain to that process. Then a saving context of a process. Kernel saves a context of process whenever it pushes new system context layer. In particular, this happens when system receives an interrupt, when a process executes a system call, or when kernel does a context switch. Interrupts and exceptions. It consists of 4 parts: interrupts and exceptions. Second, system call interface. Third, context switch. And fourth, copying data between system and user address space. So first is interrupts and exceptions. The system is responsible for handling interrupts. System is responsible for handling interrupts, whether they result from hardware, that is a different peripheral devices, from a programmed interrupts, that is software interrupts, or from exception, that is page faults. If the CPU executing at lower process execution level than level of interrupts, if the CPU is executing at lower processor execution level than the levels of interrupts, it accepts the interrupt before decoding. It accepts the interrupts before decoding next instruction and raises the processor execution level so that no other interrupts of that level can happen while it handles the current interrupt, preserving the integrity of kernel data structure. and so that it have following sequence of operations. First, it saves the current register context of the executing process and creates a new context layer. It determines the source or cause of that interrupts, identify type of interrupt, and the unit number of the interrupts if applicable. When the system receives an interrupt, it gets a number of machines. If when the system receives an interrupt, it gives the number from the machine that uses offset to the table, commonly called as interrupt vector. Contents of interrupt vector vary from machine to machine, but they usually contain address of interrupt handler for the corresponding interrupt source and the way of finding a parameter for interrupt handler. The kernel invokes the interrupt handler. The kernel stack for the new context layer is logically different from the kernel stack of the previous context layer. Some implementation some implementation use of stack kernel stack for executing process to store interrupt handler stack frames, and other implementation use global interrupt stack to store frames for interrupt handler that are guaranteed to return without switching context. The interrupt handler completes its work and return. The kernel executes a machine-specific sequence of instructions that restore the register context and kernel stack of previous context layer at existed at the time of interrupt, and then resumes execution to the restored layer. Behavior of the process may be affected by interrupt handler, since interrupt handler may have altered global kernel data structure and awakened sleeping processes. In this program, this is a algorithm for interruption handling interrupts. So algorithm in hand, that is handle interrupts. Input for this algorithm is none. Output is also none. So save current context layer, determine interrupt a source, find the interrupt vector, call interrupt handler, restore the previous context layer. This is the algorithm for interrupt handler. This algorithm shows summarizes how the kernel handle the interrupts. Some machines do part of the sequence of operation in hardware or microcode to get better performance than if all operations were done by software, but there are trade-offs based on how much of the context layer must be saved and the speed of the hardware instructions doing the save. The specific operations done by the kernel. Then this is the example of interrupts. There are different interrupts in this figure, such as clock interrupts. This is the interrupt sequence. Clock interrupts, disk interrupt, and then system call interrupts. And whenever the process is executing, entering from kernel mode, from user mode to kernel mode, so there is interruption of a system call. Then execution Whenever the process wants from the some input output device, so there is a disk interrupts. For whenever the process reschedule for its execution, then there is a clock interrupts. So this figure shows where the process issues a system call and receives a disk interrupt while the executing of system call. While executing the disk interrupt handler, the system receives the clock interrupt and executes clock interrupt handler. Every time the system receives an interrupt, it creates a new context layer and save the register context of the previous layer. Okay, next part we will see in next lecture. We'll stop here. If you have any query, please ask. Otherwise, write your roll number in chat box and leave the session.